Okay, so today I just want to make a few comments about how the zero knowledge proof stuff fits into the OSLF stuff. Um, so these are going to be sort of big picture comments, and um, over some period of time in the next few months, the idea is to try to provide some more details for some of these big picture comments. So it turns out that, with the parsimonious lambda calculus, there is a clear indication that you can have types that are related to complexity. Actually, we knew this from before. We knew this from linear logic itself, that you can have types control certain aspects of complexity. And with the parsimonious lambda calculus, you can relate the control of that complexity to complexity classes such as NP, and so there's a sense in which you can begin to have types give you information about the inhabitation of complexity classes. So making that idea precise is something that is important, so that you could, because with OSLF, the thought is that you could have, because that works across all notions of computation that we know about. Well, all the I want to be delicate around quantum computation. It should work for quantum, but there are some things that have to be modified. But certainly for all the classical computation, we can, OSLF is an algorithmic way to produce a type system. And so now, if you can find a way to lift the complexity characterization to the OSLF algorithm so that you get the complexity stratification for each model of computation, right? So that the complexity characterization is living, one level up from the models of computation. Then you would be able to, whenever you produce a type system for any model of computation, you're also producing a complexity stratification. Let me just stop there, because that's a lot to chew on. Does that make sense? Do you understand what I'm saying?
Can you explain stratification?
Yes, I'm following.
Yeah. So there's a we recognize complexity stratification like P and NP, IP, P space. These are all different complexity classes, and the complexity classes form a kind of lattice or stratification of programs.
Is NP an acronym for anything, or it's just the letters N and P?
Non-deterministic polynomial time.
Okay.
And so people believe that NP is not equal to P. In other words, what you can do with non-determinism is different than what you can do with, in terms of complexity, is different than what you can do with, deterministic programs. Does that make sense? All right, so this is a famous open question, just P equal NP. So if
can you give any examples of such complexity stratifications that are out there?
Well, one of the most important, well, sure, P and NP is a really important one. P space is certainly bigger than NP. We know that for a fact. Um, so those are examples. The zero knowledge stuff depends on NP. For example, there's a proof that any program that lives in NP. So if it lives in NP, then you can conduct proofs about claims in that model of computation, or about that sort of problem, um, with zero knowledge. So that's why, for example, NP is so important, is because it gives you this broad range of kinds of claims you can make that are for which there exists zero knowledge proofs. Does that help?
I think so. So NP being non-deterministic polynomial time, and I'm sorry, I didn't know what P stands for. That's just polynomial time, right?
The deterministic polynomial time.
Deterministic. Okay.
So the idea. So Kamislav, you asked, what can I say more about stratification? Does that make sense now?
Yes. I was just a little confused because I was just find. Can I share my screen just a second?
Sure.
To show you? So I was found in this paper, but this is a different stratification, right?
I don't know the paper. I don't know what it's talking about.
The mirrors by Angelo Braha about implementation of mirrors. And
the stratification is a general idea, right? You want to be able to, it's like filtering, right? In general, when you're talking about stratification, you're talking about, you think about a lattice, right? So you can have different levels in the lattice, because there are things that are non-comparable, but then there may be the things above them, to which they are comparable, and they're more specific. So, for example, think about the Boolean lattice that comes from the set of all subsets of a small set. Does that make sense?
Yes.
Okay, so I guess it would be class of all subsets. Anyway, so that you're yeah, sure. So then you have so you have this stratification by complexity of programs. And the thought is that if you can lift the stratification to the type level, so in particular, the stratification is an analysis, since these strata are collections of programs, then you'd like to view the type, you'd like to view the strata as somehow being types. And again, there's evidence that this works, because you can do this with linear logic. So linear logic will give you different formulae for which relate to the complexity of programs, and so which will collect certain sets of programs according to certain complexity characteristics. So the question is, can we take this idea more generally to the kinds of types that are generated by OSLF? And then in particular, identify, for example, like NP, all of the identify not just the, how do I say, you don't just carve up the space of programs according to the lattice. You're interested in specific classes of programs. So in particular, you're interested in for zero knowledge proofs, you're interested in all the programs for which you can make claims that have zero knowledge style proofs. And this may be, you know, it may be larger than we think it is, or it might be smaller in some way than we think it is. But this would give you a handle on not just all the programs in a given model of computation, but it would give you a handle on zero knowledge for every model of computation. Does that make sense?
This means, for example, if we want to use OSLF for lambda calculus, we would only consider parsimonious lambda calculus.
No, that's not what I'm saying at all. I'm saying the
Okay.
exact opposite. So what I'm saying is you can use, if you lift the complexity information up to the OSLF level, it's no longer bound to your particular model of computation. So if you can express zero knowledge proofs, the kinds of claims that you can make with zero knowledge proofs in terms of the type level, so at the level of the algorithm, then you would say, okay, well, when I apply OSLF to lambda, I get these programs. When I apply it to pi, I get these programs. When I apply it to rho, I get these programs. And so you're able to pick out, you know, interesting complexity classes across all computational models, at least all the classical ones. So the complexity information is at the type level, or the type system generation level, to be more specific. And then, you know, you can apply it to all these instances. So you get a more abstract characterization of the complexity profiles or characteristics. They're one level up. And then, go ahead.
So this will give us, for example, in lambda calculus, we will have types which we can use to specify a program that can be that can be like used as a zero knowledge proof.
Like problems in of the zero knowledge will be some kind of interactive protocol about claims that you would make against programs in that class. So, for example, you use Hamiltonian circuits as an example of a problem instance where you can make claims about the graph, such as whether or not the graph contains a Hamiltonian circuit, that where you can give protocols that are zero knowledge. Right, so a prover can convince a verifier that a graph has a Hamiltonian circuit without revealing the circuit itself. Right, so the verifier walks away convinced that there is a Hamiltonian circuit in the graph, but doesn't know what that circuit is. So now we can do that for all models of computation. Again, if one were able to conduct this program, then you could do this for all models of computation and all of the instances in each one of them. Does that make sense?
Yes. Yes.
Okay, so this is why I have been a little bit slower, is because I began to see that there's this deep connection between the OSLF work and the complexity work, especially as it relates to zero knowledge proofs. And I want to proceed in a fashion where, I'm not just focusing on a specific instance, but when I work at the level of examples, I want to be able to relate those examples back to this bigger picture. So hopefully you understand the motivations here, so that there's a huge opportunity that bears a lot of fruit. So in particular, if we're thinking about OSLF as providing a search mechanism, right? So again, the thought is that you have you can use types to search against the data repositories where you have this kind of structured data that enjoys some kind of algebraic structure, and potentially computational structure. So in other words, the formulae of any given logic that's generated by OSLF hits a data source, a repository of instances of witnesses for that logic, so i.e. programs or terms in the language that you've generated the logic for. And then you can, just by checking to see whether or not the term satisfies the formula, you have now applied the query, right? So those terms that satisfy the formula come back as those which match your query. That's the basic idea. Does everybody understand that? That's super important to understanding OSLF and its relevance to the search. Is that? Yeah. Okay.
Yes.
Cool. All right. So, go ahead.
I was going to say, basically what you're saying is you have search that is explainable, right? Meaning, not only do you have the results, but you can say how the results were arrived at.
I mean, right now there are search questions that you can't express, for example, in a relational database, because the relational encoding the kinds of relational models would be computationally infeasible. So if you want to try to, so a simple example, it turns out that you can model signaling pathways in a cell using the mobile process calculi. So for example, Aviv modeled this using the stochastic pi calculus. So because we know for the pi calculus that we can generate a type system in this way, we can now ask questions like, will this pathway ever reach this state if subjected to this environment? That's something that we can write down in the pi calculus. And so we can write down a query using types to determine that. You can't write that down in a relational model. It literally can't express the query. But you can express it in this as a type in this style. So yes, you get an explanation because you can show how the satisfaction relation was determined. but it, that's sort of gravy in the sense that you don't get any of the, it's just not a query you can write down if you were to express it in a relational model. Now, if you wanted to compare it to, instead of comparing it to relational models, which have been the dominant data storage mechanism for the last 30, 40 years, you could compare it to machine learning. So you say, I stick a machine learning algorithm on a particular data set. And there you have two issues. One is you have to train the machine learning algorithm to be sensitive to specific characteristics, right? So in other words, you have to provide examples of yes for a property or no for a property. The machine learning algorithm that we know of today are less able to discover, in an ad hoc basis, properties where we didn't know they existed. But so that's one side of it, and then the other side is explainability. So the difference between this mechanism and standard or traditional machine learning is that any formula that you can think of becomes a query. So in this sense, you can discover properties of a database rather than having to train an algorithm for properties that you think of in advance. And then on top of that, you would have you would have an explanation for why a given set of witnesses are witnesses for a given formula, whereas in the case of machine learning, we don't, it's a black box. We don't know why. So does that make sense?
Yeah, it does. Let me see if I can also relate this to something that I was reading over the weekend about the methodologies for combining object-oriented and rule-based paradigms. And the relational algebra is like a three-valued or keen three-value based implementation, I guess. Three-valued logic based. And then I was reading about this multi-valued logic or multi-valued logic approaches. And I think, but by going to the category theory, essentially we're saying it's an infinite valued logic type of a thing, meaning we can basically discover everything that is there, something along those lines. Is that correct, or is that not correct?
So I want to make some distinctions. So first of all, the algorithm exists whether or not you encode it or represent it in category theory. So category theory is an implementation detail. The thing that's nice about category theory is it provides you a language that has good abstractions, and because it has good abstractions, you can express the algorithm at the level of generality that at which it properly lives. So it's like category theory already has a good type system, so to speak. So because it has a good type system with the right layers or levels of abstraction, when you write the algorithm down in category theory, you can apply it to much broader ranges of phenomena. And then it's not so much about how many values of logic, because that's not really what we're talking about. What we're saying is that there are basically three classes of formulae that need to be accounted for. So relational accounts for one of them, which is the collection part. So again, if we return to the original intuitions behind OSLF, realizability as a principle, which has gained a lot of popularity, is going to insist that our formulae denote sets of programs that are witnesses for the formulae, or not sets, but collections of programs. So in this case, if we're writing a formula down about a JavaScript repo, then a given formula that is inhabited, in other words, there are some witnesses, is going to be a collection of JavaScript programs that satisfy the formula. So that's the meaning of every formula, is a collection of programs that satisfy the formula. So since you're gathering up these witnesses as collections, the collections themselves enjoy a kind of algebra. In particular, if your collections are sets, then you have all of the set operations. So set complement, set union, set intersection. And it turns out that all of those correspond naturally to logical operations: negation, disjunction, conjunction, respectively. And what relational algebra gives you is those operations. So it talks about collections. That's really the operations that relational algebra is good at, is those operations. There are certain representational aspects that allow it to do things like joins, and but at the end of the day, all of that machinery is about the collection operations. And in particular, it's about set-based collection operations, because relations are properties of sets. That's the way we think about them. But you could have other collections. So linear logic gives you a different kind of collection. So it gives you sets of sequences. So you can think about that in terms of instead of a data structure like a power set, which is where relations naturally live, it's a data structure called a quantale, which is the set of all sets of sequences. So that's a different data structure, and it will give rise to different logical operations. And so that's just the first class. So we haven't even talked about the other two classes of formulae. So the first class is just, what's the structure of the container in which you collect your witnesses? Right, so it could be sets, it could be quantales, it could be something else, right? So bags, lists, and when does the container part of it have the requisite structure to really consider it a logic? So that's a separate set of questions, but hopefully I've given you some intuitions. Does that part of it make sense? Because I'm about to jump on to the next bit. Does that make sense?
Yeah.
Okay. All right. So then the next bit that relations don't see unless you explicitly code it into the relations is the structure, the algebraic structure of the terms. So every theory of computation comes with, well, without loss of generality, every classical theory of computation comes with a term language, right? That's how you build. It's the language in the syntax for your programming language. So it turns out that also gives you a class of logical formulae. So you can think about this in terms of the syntax trees. So you could say, I'm interested in all the trees which have a par at the top. So I don't know what the structure but beneath the par is. I know they're all going to be processes on either side of that par, but the top of all of these syntax trees is a par. And then you could go on. You could say, and then in one side of the par, the top is a for comprehension. And in the other side of the par, the top is an output of some kind. So again, you'll have lots and lots of things that are for comprehensions and lots of things that are outputs. So so that kind of query would give you, it has the syntax tree that's a par at the top, and the next level on one side is a for, and the next level on the other side is an output. So that kind of structural query would give you all the programs that at least have the possibility to interact. You'd have to have more information, like it's a for comprehension listening on a specific channel. Then we don't know the rest of it, but it is listening on a specific channel. And then an output that's listening on a specific channel. We don't know what it's sending, right? But so then with that refinement, that query over your data source would give you all of the syntax trees that definitely have a regex embedded. They might have other things, but they are definitely able to interact. Does that make sense?
Yes.
Okay, right. So that class of logical operations comes from the structure of the terms. It doesn't come from the structure of the collections of terms. You see, they're different. One is coming from the collection part, and the other is coming from the term structure part.
So one question came to my mind is, for example, if we use relational database to store this kind of information, I'm a little confused to distinguish. We can basically store AST in the database, and we can query in this way. But you're not talking about in this way, right?
No,
I'm mixing things.
you could do that, but the next class of formula is where it would break down. So you certainly could do that if you encoded the structure of the terms in your relations. You could do that. Now it turns out that will be really complicated. So the structure of your queries will be very complicated, and then on top of that, the queries will have very bad complexity characteristics.
Yeah, I tried that, and yeah. With SQL, first of all, you need to use some kind of recursion, which is not directly,
Exactly. So it will be terrible from that point of view. And then it breaks down entirely for the next class of formulae, and that are the modal formulae. So after this, then this. So after the thing interacts through an input, it moves on to something that matches this spec. So that behavioral information is now going to be computationally infeasible. I mean, you can you could do it potentially with the relational encoding, but it's going to be prohibitive computationally. It won't work from a, like making it practical, it won't work. So, so that's why the relational model is not so good. Whereas just following the structure of, so someone hands you a model of computation, they've given you tons of information. They've said the syntax of the programs, they've said what the rewrite rules are, they said what the structural equivalence is. All of that information they gave you, right? So when someone tells you the Java spec, right, they tell you the syntax for well-formed programs, and then they tell you what the transition steps for the Java virtual machine, right? And then implicitly in there is a set of equivalence relations over the syntax and the registers of the JVM. And so when you have all of that, then you have a ton of information that you can then utilize to query about the structure and the evolution of Java programs. And so you should use that, right? So use that to build your query language and the mechanism by which you search it. Does that make sense?
Yeah, yeah.
Okay, good. So now the next piece of the puzzle is you'd like to be able to have people issue queries like, does this graph have a Hamiltonian cycle, without information come back about the specific information about the witnesses. So you're going to obscure details.
So Rebecca, are you supposed to share screen?
No, I'm not sharing screen.
Okay.
I'm just talking, right? I'm just trying to give a big picture overview of how, like, the more I go into the zero knowledge stuff, the more I see that the connections to OSLF are very profound, and they provide important advancements over the search capabilities. Right. So ultimately, you want to be able to say, for example, for some healthcare data, is this property of this population true? Like, for example, all of those who took the mRNA-based vaccines, 15 years down the road, they develop symptoms X, Y, and Z. Without revealing which individuals developed those symptoms, right, or without revealing personally identifiable information about individuals that develop those symptoms. Does that make sense?
Yeah, yeah. So we can also search, for example, someone can say, I have large database of programs.
Yes.
And for example, if we need some part of the program, we can basically search this database without revealing. Someone can give us a search without revealing the programs, and we can find the match, and then we can basically negotiate for
that's exactly right. That's another very good way of saying it. So I have programs which satisfy your query, but I'm not going to tell you what they are unless you pay me. And then, as a client, you are convinced that in fact these programs do satisfy your query, but they're not. We're not going to give them to you because the reason you're asking is because they're valuable.
Yeah, and we can also know performance of these programs. Is it something that we are interested in or not?
Correct.
Right.
Yes, exactly. The complexity
Mm.
characteristics would also be a part of what's going on. Exactly. Now, I want to point out that, you know, there's never a free lunch unless you meet some guy who's giving out loaves and fishes. But so certain of these kinds of queries may have bad running time, but bad running time is better than I can't even write down the query. And especially as we move towards a fluctuation in hardware, right? So we're about to enter into this time period when there's a great deal of volatility in hardware, in the sense of how much power it consumes and how it performs against that power curve. Right. So just with ordinary classical computation, we are about to see a big shift. But then on top of that, we have, you know, the emergence of quantum supremacy. So things that are bad running time now, especially of the kinds that I'm thinking about, like with the PAR example, that will have bad running time. Because, you know, without optimization, you have to go, you really do have to check all pairs, right? And so you have to hope that the subformulae, you know, means that the pairs are sparse, so you don't have to do as much checking. But that said, you're with the quantum, you could check all those pairs potentially in parallel, right? And so, and that could be done all at once, right? So the shift from I can't write this query down to I can write it down, but on current hardware it has bad running time, is not necessarily, I mean, first of all, I think it's an enormous advance. But second of all, you know, with the hardware shifts that are coming down the pipe, we're going to see the possibility that that those bad running times dramatically improve. So this is kind of the framework, the kind of conceptual framework, both in terms of motivation and in terms of you know, sort of the how all the pieces fit together, the architectural pieces that, you know, I'm thinking about right now as I work on the zero knowledge stuff. So hopefully that's making sense. So I just want to make sure that as I'm working on these examples, I'm working on them in the light of how it informs the rest of the picture, because it's huge, right? I think we can agree that the opportunities here are they're very large.
Yeah.
Cool. That's all I have to say today. Hopefully I will return back to showing some fun mathematics next week, but I think there was some brain candy in this as well.
Yeah. Can I also ask you?
Yeah,
go ahead, Tansla.
I was just want to ask you how we can think about OSLF on some kind of meta level. So this is like a concrete question when we ask, I need some program to combine with my existing program.
Yeah.
But can I think more in a meta level and explore, like, ask OSLF as a query? You know, I want to have answer to my question. Can you explore all of the possible programs? Or
well, I mean, you can certainly think about it like transferring from one programming domain to another, right? So that's something you can definitely do, right? So you know, I'm writing, let's say, in Lambda, but I'm only interested in concurrent solutions to an algorithm that I'm going to compose with my programs.
Yeah.
So that's very possible. And more generally, the moving over in when the implementation of this OSLF approach is category theoretic, then for example, ideas of reduction turn into the existence of functors. And so that has a way of taming, how do I say this? So like, it's relatively it's a kind of wild west to talk about reducing, for example, SAT to some other problem, because it's going to be done ad hoc. It's like you're just going to say, okay, well, I've got satisfiability and I've got my particular computational domain, and then I have to figure out by hand how to encode SAT into my computational domain, right? So it's going to require human creativity. But if you have a categorical representation, especially through the type mechanism, then you could have these type guided translations, so type guided reductions, which kind of force the translation to respect certain characteristics. So it has a much better chance of being algorithmic. So you can so the aim would be to algorithmically produce reductions from, for example, some problem in NP like SAT to other computational domains, and thereby show that they are in fact in NP.
I see. Can I also ask you, I was thinking about matching enrolling, but so can it be this possible to match on the behavioral types? Not. So I was thinking about that, and I'm not really sure.
Wait, can you state your question again, please?
Is it going to be possible to match on some specific behavioral type? For example, now if I am writing the pattern enrolling, can I also say, like, can I specify the matching type inside the pattern? Because when we say
I see. Yeah. So it turns out that the pattern matching and the structural types are one and the same. They're exactly the same. It's the same algorithm. This is something that Kyle also observed. Right? We've known this forever. Pattern matching and structural type checking are the same thing.
I see. Okay.
Okay. Thank you so much for your time.
I have a tangential question, and if it is too long, maybe we don't have to take it now. But what I'm wondering is about the database technology and the evolution of database technology. So before relational databases became established, for a period of time, there was the hierarchical databases and the network databases for a very brief period of time. And now, of course, with the relational, then we came to the key value stores and the column-oriented databases and all that. But do you see something like a network database either becoming important or being implemented, given that we seem to discover more and more that the world is a network, especially because of the internet, or do you not see that?
You mean graph databases?
Yeah. I mean, they are already coming up, the distributed graph databases.
They don't have Roland.
I mean, so you know, in general, if you have if you have an algebraic theory of graphs, then we'll generate a query mechanism for it. And depending on the way you view graphs, and there are lots of different ways to algebraically characterize graphs, then you know, we'll give you different views on the graph information. So I think that's very much a special case of what we're talking about. Yeah, just, you know, so for example, Philippa Gardner and Luca Cardelli and Giorgio Gelli came up with an interpretation of graphs in pi. And then, so you can write down graphs in pi calculus. It's a very straightforward thing to do. I leave it as an exercise for you guys to figure out how that's done. And then, because they had, you know, the spatial behavioral types, they could then turn the spatial behavioral types into a query language for graphs. And then Giorgio took that and kind of distilled it down and optimized it. And, you know, they had a pretty nice graph database that is derived from first principles. So we're just taking that idea, but we can do it not just specifically for a pi calculus encoding of graphs. You can do it for whatever your theory of graphs is. Like, you know, I have the toggle theory of graphs. So because of the algebraic representation of graphs via toggle, you can automatically generate a type system for toggle, and then you get a graph query language. Does that make sense?
Yeah. Maybe we could, I would like to read some of those papers, but we can take that in Discord.
Sure. Yeah. Just Google, you know, Gardner, Cardelli, and Gelli, and graph and pi calculus, and you'll get their papers.
Great. Okay. Thank you.
Sure. All right. Thanks to all, and we'll see you in Dev Stand Up shortly.
Thanks, Greg.
Thank you. Bye-bye.